Alright, welcome to our last video in Module 7, where we will be going over how to run and interpret an output for a two-way ANOVA in SPSS. Specifically, we are going to be covering a two-way independent ANOVA, where we have two between subject variables. So, our example research scenario is that a researcher wants to determine if the effect of education level on interest in politics is different between males and females. While this is not a kinesiology example or a health science related example, this is the run that is provided on the Laird Statistics website, so it matches all of my screenshots. In the kind of purpose statement, I've identified our two independent variables, which is education level and sex, or difference between males and females. And then we are comparing these groups' interests in politics. So we have collected 60 participants, 30 males and 30 females, and then we randomly sampled these people and then equally split them based on their level of education. So school is kind of like considered high school. College would be like an associate's 2-year type of degree, and then university is considered like a 4-year degree. So equally split, we have 10 participants in each category for each gender or each sex. Okay. The dependent variable is that the researcher had participants complete a questionnaire that assessed their interests in politics, which they called the political interest scale, and then participants could score anything between 0 and 100. Higher scores indicated a greater interest in politics. So that's the dependent variable that we have measured, and there's one measure for each participant. So, as an example of what we call this test, because we didn't have a very clear-cut example in the lecture notes, we can break this down by looking at the independent variables. So we have independent variable A as education level, and it has 3 categories or 3 levels: school, college, and university. Then we also have independent variable B, which is sex, and that can be split into males and females, so that's 2 levels. Right? When we name our two-way ANOVAs, we have to have 2 primary components that indicate the type of ANOVA. The first being the number of independent variables, the second being the type of samples, and then lastly, you just say it's an ANOVA, right? So number of independent variables can be referred to either as a two-way, or it can be listed as a level-by-level comparison. So in this case, we have a 3x2. Okay. We also need information about the type of samples. So for this week, we have independent ANOVAs. So we could refer to this as a between-between ANOVA or an independent samples ANOVA to indicate that both of our independent variables are between subject factors. So different namings that we could use is like a two-way independent, a two-way between-between, a 3x2 independent, or a 3x2 between-between. Right? There's various combinations that you can use as long as you have the number of independent variables identified as well as the type of samples, then you are good to go. Okay? So when we set up our data, it'll be very similar to a one-way ANOVA. But we're just going to have a second independent variable that we are going to list as our nominal factor. And then also similar to our one-way ANOVA, in the values column in our variable view, we need to indicate what values mean and what labels they are attached to. So for our sex variable, or gender as it was listed in the example, 1 equals males, 2 equals females. And then for our education level, 1 equals school, 2 equals college, and 3 equals university. Once we have our data set up, again, we're going to assume that we have normally distributed dependent variables with no significant outliers, we need to set up the test. So to do this, we go to Analyze, General Linear Model, and then Univariate. Okay. General linear models are going to be used when we have several different types of scenarios. So univariate tests are going to be for our two-way independent ANOVAs. Multivariate tests would be if we have multiple dependent variables. So univariate, uni meaning one dependent variable. And then repeated measures, all of our types of repeated measures tests will go through this option. So both a one-way and a two-way repeated measures, as well as a mixed two-way ANOVA. So the rest of our tests for this section, other than the compare means for the one-way ANOVA, are going to go through the general linear model. All right, so the next step would be to identify your variables. So once you choose the univariate test, this should be the window that pops up. Your dependent variable will go in the dependent variable box, and then your independent variables will go into your fixed factors box. From there, we will set up our post hoc tests, which is going to be under EM mean. So what this stands for is estimated marginal means. You might be tempted to go to post hoc, but there's a limitation in SPSS where the interaction effect does not get tested in the post hoc window. So we go to estimated marginal means to calculate all of our post hoc tests or all of our pairwise comparisons. Once you click on that button, it'll bring up a window. We're going to put all of our variables and transfer them using the little arrow, transfer them over to this box that says display means for. You'll then check the box that says compare main effects, and then this is a drop-down menu in which you'll choose Bonferroni. So Bonferroni is a specific type of adjustment that is used when we look at pairwise comparisons. So similar to Tukey's test, there's certain calculations that happen within the software for that adjustment. The same thing goes for the Bonferroni. Right, it's just a slightly different adjustment. And don't worry about what actually happens to the data. That's kind of beyond the scope of this class. Just know this is the adjustment that we're using. So once you get that, you can click continue. That will take you back to the univariate window, and then you'll click the button on the side that says options. In here, you'll be able to choose different calculations that you want included in your output. We do want descriptive statistics. That'll give us the mean and standard deviation and standard error of the mean, confidence intervals, etc. for our groups. Estimates of effect size will show us the calculated effect size. In this case, it'll be not omega squared. We'll get there at the end. And then we also need homogeneity tests because we have between subject factors. So those three boxes should be checked. You can click continue. That'll take you back to the univariate dialog box or the main window. And then the last thing at the very bottom of that window, you'll see a paste button. Click on that, and it should bring up a syntax window, which we haven't messed with too much yet. So the three windows that you can open in SPSS are an output window, a dataset window, and then a syntax window. This is what the syntax window looks like, and it's basically coding, which is a lot of fun. But in the syntax window, SPSS does not automatically include our simple main effects which is what they're technically called, but it does not include our pairwise comparisons for the interaction effect. So we have to insert them ourselves. Now, usually what you'll see when this window initially pops up is kind of this beginning part, and then it'll have EM means, tables, gender times education, or whatever your two independent variables are, and then it'll stop there. So I'll do an example of how we actually change the syntax in SPSS, but what we're adding is this compare gender using a Bonferroni adjustment, and then we're also going to add another layer to this where we're comparing education level using a Bonferroni adjustment. And so what this is going to do is it's going to give us pairwise comparisons for a comparison of independent variable B, which we said was gender, within education level. And then it'll also give us a comparison of independent variable A, which we said was education level, within gender. So from here, we then can click on the Run tab and then do all, right? And that should generate your output. All right, so we have set up our test, check. Now we can look at our assumptions, which for the purposes of this class is just limited to our homogeneity of variance assumption, which is tested with Levine's test. So when we get in our output, we'll have Levine's test of equality of error variances, which is still the same of equal variances, okay? And it even tells you down at the bottom, test the null hypothesis that the error variance of the dependent variable is equal across groups, okay? So the one you're going to focus on is the row that says based on mean. So we can see here our p-value is listed for Levine's test. Again, the variances of each sample is the same as our null hypothesis. Since we have a p-value that is greater than our alpha level, we would accept the null hypothesis and say there are equal variances between groups for both sexes and education levels. So the way that this works is that all the independent groups, all of the variances are calculated for males, all females, all school, all college, all university, right? And then we take those variances and then compare them together to get our p-value for Levine's test, which is why we only have one p-value. This will be different once we get into a mixed ANOVA, but for now, one p-value, and we can say we have accepted our homogeneity of variance assumption. Now, if you happen to violate homogeneity of variance, in which case maybe this value ends up being less than 0.05, we'll still note, hey, we rejected homogeneity of variance, but we're just going to keep running through the test so that way you get experience practicing all of the procedures. Alright, so now we've checked our assumptions. The next thing would be to interpret the ANOVA results. And you'll recall from our lecture, or part 1 of our lecture, that when we have a two-way ANOVA, there are 3 main effects that end up showing up in the ANOVA output. So usually when you have a two-way ANOVA in research, most people are interested in the interaction effect, and oftentimes that's going to be the p-value that's reported. But sometimes people are also interested in the main effect, so sometimes you'll see all 3 reported, sometimes you'll see just the interaction effect, sometimes you'll see if there's no interaction effect, people report the main effects regardless. So there's a mix of what you might see in the literature, but generally speaking, for our class, we're going to list and interpret the p-values for each of these 3 main effects. So we'll focus on the main effect of our independent variable A, which in this case was our education level first. This will be in the test of between subjects effects table, and you'll see gender, education level, and then the interaction between the 2 variables. So all of the p-values, excuse me, all of the p-values for our main effects are going to be in the same tested between subjects effects table. For this, we can see the p-value for education level, right, is in this highlighted row under the sig column. So p is going to be less than 0.001, which is less than 0.05, which tells us we can reject the null hypothesis. And the null hypothesis for the effect of education level on our political interest is that education level has no significant effect on political interest. Right? So we're looking at education level independent from gender. So another way that we could interpret this is that there is at least one significant difference between education levels regardless of sex. You could also say education level has a significant effect on political interest regardless of sex. I'm kind of leaving this last part up to you guys. You can include it, you can not include it. I've seen both in research, so I feel like it's kind of just personal preference on how you report this. But we'll note that since we have a significant main effect, right, so P was less than 0.05, this does require that we look at the post hoc test to see where the differences or which education levels are different from one another. So we'll kind of put that on pause for right now. But we've now checked the main effect of independent variable A, or education level. Now we need to check the main effect of independent variable B, which is gender. So in the same table that we just looked at, we're now focusing on the p-value for gender, which is 0.448, which is greater than 0.05. So we're going to accept the null hypothesis that gender has no significant effect on political difference, or on political interest. So another way you could word this is that there are no significant differences in political interest between males and females regardless of education level. Now, since we don't have a significant main effect in this scenario, post hoc tests are not required for gender. Okay, again, you only need post hocs if you have a significant main effect. So that checks off the first two main effects. Now we can look at the interaction effect, which is going to be seeing if there is a significant interaction between education level and gender. So in our table, again, same table we've just looked at in the last several slides, gender, this is an asterisk. It's a little bit small in the slide, but that's what it'll show up as in SPSS. So it'll be your independent variable A times B. In this case, they were flipped, but that's okay. And then we see our p-value is 0.002. So this will indicate, right, our null hypothesis is what's being tested here. There is no significant interaction effect between sex and education level. P is equal to 0.002. That is less than 0.05, so that indicates we should reject the null hypothesis, in which our interpretation could be there is a significant interaction effect between sex and education level. Right? And again, because there is a significant main effect, we need to look at the post hoc test for the interaction effect now. So our fourth step in our process is to check the pairwise comparisons. And now I've kind of broken this down from our original checklist because we've identified which main effects were significant. We said the main effect of independent variable A as well as the interaction effect were significant. So therefore, these are going to be the three pairwise comparisons that we're interested in looking at in our output. Okay, so then for the pairwise comparisons for main effect of independent variable A, which was education level, will look something like this, right? So we have very similar to a one-way ANOVA in our post hoc test where we're looking at differences between pairs of our independent variable groups. And again, there will be redundancy. So if we look at school and college, that's repeated with college and school. Okay. All right. So based on this table, we have our p-value column, or our sig column, and we can note that the significant pairs are all of them, right? So all pairs are significant. School is significantly different from college, school is significantly different from university, and college is significantly different from university. A shortcut is just to say all pairs are significant, right? And the interpretation would then be there are significant differences between all pairs of education level regardless of sex. Okay. So that takes care of our first set of pairwise comparisons. The second set of pairwise comparisons we're going to be for looking at levels of independent variable A within levels of independent variable B. So what this means is that we're going to look at differences between education levels within gender. Okay, so this is, if you're thinking about the syntax, right, compare gender is telling you which independent variable you have investigated. So, actually, I guess I should have mixed these. So, oh, nope, we're okay. Never mind. Nope, I should have mixed them. I'll fix that on your copy, that way it's not confusing. But this one we're looking at the comparison of gender within level of education. So technically this is looking at the comparison of independent variable B within levels of independent variable A. And similar to our other pairwise comparisons table, we have a sig column with our p-values. And we can note that the significant pairs are between males and females in the university level of education. Okay, so our interpretation of that would be there is a significant difference in political interests, which is our dependent variable, between males and females who have a university education. All other pairs were not significant, but this is probably one of the reasons that our interaction effect was triggered as significant in our tests of between subject effects table. We then can look at the other interaction effect comparison, and technically this would be flipped, so I'll again change that on your PowerPoint. But to look at the other comparison, now we would be flipping our columns and say, let's look at the differences between education levels within a specific gender. Okay, so this would be related to the syntax compare edu level in that syntax step that we did earlier. We have a p-value column, which if we kind of skim through all of these, all of them are significant. So all pairs, if we ask which pairs are significant, all pairs are significant. And the interpretation would be there are significant differences between all pairs of education level for both males and females. All right. So that takes care of our post hoc or pairwise comparisons. Again, only if your ANOVA results for your main effects are significant. And then we need to calculate the effect size. Now, the nice thing about the univariate setup is that it will automatically include an effect size calculation for you. Instead of us calculating an omega squared, there is a different calculation that SPSS uses in the univariate test, and it's called partial eta squared. Eta being this fanciful N-looking symbol. The nice thing is that omega squared and partial eta squared are interpreted using the same coefficient values. So 0.01 is still a small effect size, 0.06 is still medium, and 0.14 is still large. And we can find our effect sizes listed in the tested between subject effects box. Specifically, these are going to be accepted for our main effects for each independent variable separate from one another. So if we look at the main effect for sex or gender, we can see our partial eta squared or effect size is 0.011, right, which is going to be related to a small effect size. And we can say there's a small effect size between males and females, or like the difference between males and females for their political interest is small. For education level, we have an effect size of 0.879, which is greater than 0.14, so we would say there's a large effect size between education levels, since that was the independent variable of interest. When we get into our interaction effects, we have to report, instead of from the main effect table, so you can see there's a partial eta squared listed for the interaction. If we had a non-significant interaction, then we would report the partial eta squared for that non-significant interaction. Because we have a significant interaction, we're going to actually report from the univariate test results, which will give us kind of divided effect size values for each of the groups that we have been comparing within. So this univariate test came from comparing education levels within gender. So our effect sizes are listed on the right-hand side of the table. And we can say for the male row, right, our effect size was 0.836. This would be interpreted as a large effect size just based on the value that's provided. Okay, and we have a large effect size for differences between education levels in males. Okay, so again, because this is an interaction effect, we were looking at comparisons of education levels within genders, right? So we have a difference between education levels in males because that is the effect size associated with our male category. For females, we have an effect size of 0.708. So again, this would also be a large effect size for differences between education levels in females. For the last interaction, if instead we were looking at the comparison of gender within our level of education, we still refer to our partial eta squared on the side. And for school, we have an effect size of 0.029, which is relatively close to 0.01. So we'll say we have a small effect size for differences between males and females in school. Okay, so difference between, right, comparing males and females within the school level of education. For college, our effect size was 0.017, again, small, for differences between males and females in college. And then for our university one, that was 0.199, which is a large effect size. Okay, so large effect size for differences between males and females in university. I do want to point out it's important to separate the p-value from the effect size. So p-values indicate significance, effect sizes indicate how large the difference between your group means is. So you can have significant differences that are small, medium, and large, right? The effect size just tells you in the terms of the unit you've measured how large is this difference, right? And then you can determine are large differences considered significant or are small differences considered significant. But having a small effect size does not mean that you won't have a significant difference. So when you interpret the effect size, you're just saying it's small, it's medium, or it's large. You don't need to integrate the significance part in it. It just is informative in research by telling you kind of the magnitude of the difference that might be needed in order to show significance in your p-values. All right, so that concludes our SPSS procedures for our two-way independent ANOVA, and you guys should be set to go for your activity videos.